and it was working. So I will show that one. Okay. So from first in onwards, I'll show that analysis. Okay, so first I down actually if you have your own data, you can continue with that, and if you that first data set is it work it is if it is working, you can continue that also. Okay, but here I'm not getting and I cannot continue with that. So because of that, I'm downloading the data that is. I downloaded from Geo dataset. So Geo database. Okay. So this is the dataset SRP 240 640. Okay. So you can click here. So this is the details like title is like RNA-seq analysis of significant transcriptional changes within the livers of patients with alcoholic hepatitis. And the summary is like this is the alcoholic hepatitis. Sorry, the design is like expanded livers from patients explanted livers from patients with acute alcoholic hepatitis that sampled by RNA-seq and relative gene abundance was compared to samples derived from donor livers. Okay, here you can see the 10 samples. So this is the patient sample and this is the donor patient. This is the alcoholic hepatitis patient and this is the donor patient. Okay, so here we are downloading three. Like here we are setting this as control, three samples as control, and this is the patient sample. This is the patient sample. So here we are downloading three samples here, like 58, 59, 60, and 53, 54, 55. So we had to download that. So for downloading, we had to select SRA run selector. Slow here. You can also do with me. Okay. So it will show like this, and you can select the data like if you are okay. If you can do full, if you can take full data, you can do like that. But I'm taking here like three control and three sample, three treated. Treated in the sense patient data. So okay, first three and 50. 850. Okay, selected. Okay, then you can click here accession list. So it will download a list of file, text file. Okay, so you can open Galaxy. Okay, this already I done. So this is a result till DSeq annotation. It's done actually. So okay, I'm uploading the data. Just drag it here, then start upload. If you're not able to follow, you just ask doubt. Okay. Okay, then close it. Then you can see the upload is going on like, okay, so it will take 2 3 minutes time. So here it's already I uploaded. Uh, so here it's uploaded. Okay, so then we can like abstract. 1 minute. Sorry, download. Okay. Okay, this faster download and extra reads in FASTQ format from NCBI SRA. Click it. Then you can, okay, instead of SRR accession, you can go list of SRA accession one per line. Okay, so here it will come. You can select, yeah, then run tool. So it will download the data like this. Okay, so here it will take some time, like downloading. I think it will take 15 minutes or 15 to 20 minutes time, or sometimes half an hour time. So okay, after you can download like this, so you will get a parent data, single end data, and other data like first q dump and first q dump log file. Okay, so after downloading you can continue the same steps what we discussed in last session. So you already know, no? First step is like quality control. Uh, okay. Is it sharing or not?
Yes, we can see.
Oh, okay, okay.
I think everybody can follow.
And
Can,
nobody is responding.
you
That's
can
why I
respond. That's
was.
why I responded.
Okay. Sure. Okay. Yeah, it is.
Yes, yes. One
Sorry.
comment came. As ma'am following.
Okay. Uh, okay. So this data you will be downloading like this, and after that you just continue with fast QC. Okay. So fast QC I did like, okay. So I'll show that fast QC. Fast QC. Then you will get this data here. That I think this data is like a single line data. So you can select here single line data. Then so others are like default. Keep it as like default parameters. Then you can run the tool. Yeah, it's running now. Okay, so it will be a collection of data. So if you are clicking here, you will get that. I mean list of data. I mean how many total we downloaded 6 data, right? So you can sorry, you can see here raw data. Okay, so the result will be in web page. I mean that graph and all you can see in this fast QC collection web page. Okay. So this is like you can view in different plot. If you want to campaign and view it, or you campaign and view it in a single report, after fast QC you can do multi QC. Okay, so multi QC, mainly it campaigns a campaign and it will show the result in a single report. Okay, main if you are doing multi QC, you can easy to, I mean, you can easy to compare the data. Then, as last session we discussed, after first QC, so multi QC is optional. Okay, so for analysis. So otherwise, first after first QC, you can continue the trigonometric. So that also we discussed in last session. So fast QC already discussion done, right? So that's why I'm not showing the result today. So I'm continuing the trigonometric. Trigonometric. Okay. So trigonometric again, you can select as a single end. This is a single end data, so that's why I'm selecting single end. Okay, if your data is a parent, you can select parent. Then, okay, single end data, first you dump that. So it will show the collection of that data, single end data. Then trigonometric, yeah, others you can keep it as a default parameters. So again, run the tool. You can run the tool, and it will run here. Okay. So a list of 6 data. It will be showing like this. Okay. Then after trigonometric, what we did is like mapping, right? So for mapping, we had to download the genome and GTA file from Ensemble database. So we are not using default genome here. So we are just downloading the mapping, genome and GTA file from Ensemble database. So since it is a human data, we are downloading. Not ensemble, the ensemble. So here we had to download the full genome FASTA, genome as a FASTA and GTA file. Okay. So here I can click human. So here you can see download FASTA files for genes and also GTA file. So here you can download the FASTA file. Click it. Then click the DNA. Then you can download the top level file. Okay. So here click copy link address. Then you can upload like this. Upload data. You can download it separate and upload. That also you can possible. Otherwise, you can upload the data like this. Paste and fetch data. So new file. Since it is a FASTA file, you can you can give a name human FASTA.
Dr. Vijana, one question is there.
Okay. So what is the question, sir? So it will,
I will tell. I will tell. I will tell. I will tell.
okay.
Ma'am, after trigonometric step, do we have to again perform fast QC analysis to check the quality of trimmed
Yeah.
sequences?
Yeah, you can check first QC for, but actually no need to check. It will be cutting nicely, and it will be okay. You can check if you are doing a research or a PhD work or research. You can check, and you can like even after fast QC, you can do multi QC, and you can compare the result and I mean check the result. Okay. So that, yeah, that is actually no needed, but you can check it. Okay, so I'm giving a name like a human FASTA or any name, FASTA file, any name you can put. So here I'm pasting the link. Then start, start to download. So here it's uploading that FASTA file, I mean genome file is uploading here. So you can see here. Okay, so like that again that recently.
Hello, ma'am.
Huh.
Ma'am, can you again show how to download the FASTA file?
Okay, just go
Okay.
to ensemble.
Yes, ma'am.
Okay, actually we are analyzing a human data. Okay, so
Okay.
we need to download the human genome.
Hmm.
Okay, so click here. So this is the human genome.
Okay.
Okay, then here genome annotation files are there. That is, this is the FASTA file, full
FASTA
genome
file.
file. Huh, FASTA
Okay.
file, and here you will get GTA file.
Okay, ma'am.
Okay, so click here like download FASTA file.
Hmm.
Okay, then click DNA.
Okay.
Then you will get, just scroll it, and end of the end you will get a top level file, top level FASTA file. That is here, last one. So
Okay.
before that the readme file. Okay, then
Okay.
copy that link address. Copy that link address. Right click and copy that link address.
Hmm.
Then go to, I mean upload data. Here upload data one symbol is there, no? So upload data. Then you can click here, paste or fetch data option is there, no? Paste and
Okay.
fetch data. Click that. Then here you can put the name like which file it is. So I already put like a human FASTA. So you can put FASTA file or something like that.
Okay.
Okay. So here you can put, and then here you can paste it and start it.
Okay.
So okay. So same thing, you can download. Okay, download GTF file here. Okay, download GTF file. So here you will get the GTF file of GTF file before the readme file. Okay, so again click copy link address. Then you can go to upload data again, paste or fetch data. Okay, new file. Here you can put human RTF file or something. Okay, human RTF file. Oh, sorry, RTF GTF file. GTF file. Okay, so your paste, then start it. Here you can okay. Here you can see it's uploading. Okay. So FASTA QC, it's finished now. No, it's not downloaded yet. So after that, FASTA QC it will finish, and then Primomatic. Then we downloaded the human FASTA. I mean, this is full genome, and this is the GTF file. So next we will start the mapping alignment session. Okay. So for mapping, I tried star as well as HiSat. So star it is still running. 2 days ago, here you can see RNA star. 2 days ago I started, but still it is running. So I just did HiSat 2. Okay, HiSat 2 it was working fine, and it took I think half an hour time. So if you want to fast result, you can go for high sat, and if you are if you're able to do star, then you can go for star. Star always it will take time. Okay. So after this one, you can go for high set. Even after this, you can do multi QC and you can check the result. Okay. So then we are checking high set 2. So this is the fast and sensitive alignment, especially designed for, RNA-seq. Even a star is also especially designed for RNA-seq, but mainly it is taking time. Okay, so HiSat. Then use a built-in genome. So we are not using built-in genome here. So here use a genome from history. Okay. Then you can, it will automatically show here. Select the reference genome FASTA file. Okay. So already I downloaded here. So it will show like this. And this is paired library. So single line data. Okay. Then thermomatic collection. It will show like, okay, thermomatic collection. So that this input is like a thermomatic result. Then you can, okay, if it is a forward, if you have any information like regarding this strand, you can select forward. Otherwise, you can keep it as unstranded. Okay. So F means a read correspond to transcript. R means a read correspond to reverse complemented counterpart of the transcript. Okay. Uh, if you know that, you can select forward. Then summary option. This and all you can put it as a default value. Spliced also. So the reference genome. This genome from history. Okay. Everything is over now. Okay. Then you can run the tool here. Okay. So by clicking here, you can see the result BAM file. It shows like the result will be in a BAM file. Okay. It will take, I
Dr.
think,
Vijana, one
half.
question is there. Ma'am, what is the use of human GTF file you have downloaded?
Genome annotation file. It will be useful for doing feature count. Annotated annotation file. The human FASTA is like full genome. Okay, so by doing, feature count, it will be the tool will ask that GTF file. So that's why I downloaded. Okay, so okay, high set two done. Like it will show, it will take time. So everything will take time. Okay, so if you want to do star, that also you can do. Okay, that if you main thing, if you are doing a PhD research or high end level of research, you just do all the tools. Okay, with the same data set. Okay, then compare the result, and which tool is giving a better result or a good result, then go with that. Okay, then do research and continue with that tool. Okay, anyway, especially in PhD students, like you just compare the result. Otherwise no, it will be like okay, the result will be good, but that will, for research anyway, you have to compare the result. Okay, so here after high sat, we had to do the, okay, till high sat, I think last session we did, right? or till feature count we did, I don't know. Even I also forgot everything. Till high set we done, or feature count?
No response.
No response. Okay, then okay. After completing high set, we had to do the we had to count the data. Okay, so using feature count. So for that, uh, okay, for that also, so many tools are available, and but in the case of RNA-seq, you can use feature count, so it will be giving a good result. So next we had to do the feature count. Feature counts. Okay. So feature counts means it's a widely used tool for me. It using for counting the reads or alignment to genomic features such as genes, exons, or other genomic regions. Okay. Uh, so here we can select the HiSat result. Okay, so here I did RNA, I mean star, so that's why it shows like that. So here you can select, click here, and you can select the HiSat result. It will be it's a BAM file. Okay, BAM file. Then okay, you can keep it. Already we selected forward standard, so you can keep like this. Then genome annotation file, you can select a GTF file in your history. Okay, so this tool it will ask. So that's why we downloaded the genome annotation from genome annotation files from Ensemble. So here you can click here in your history. Then it will show like this human GTF file. If it is not showing, you can browse the data sets from I mean folder. Okay, then genome feature type filter, you can keep it as exon gene ID. Okay, then yeah, output format will be like this. Okay, create gene length per. Okay, this and all you can keep it as a default parameters. Then you can run the tool feature count. Yeah,
Ma'am,
it's yes.
ma'am, I have human genome data from the previous
ah
lecture that you made us download, and so I
that
can.
also you can use.
Yes. So when I used it and I used this GTF file for annotation, they show that it is unavailable. GTF file unavailable.
No, no, no. That it's showing like that, but it will take.
Okay.
It was working for me.
Okay.
That
Okay.
also you can take. Yeah. Okay. So feature counts. It's successfully added 6 jobs to the queue. So it's running now. So after completing the feature count. Okay. Here we did feature count selection. So it will give the count data, okay, and feature count on collection. Okay, by clicking you can see the summary. Okay, then feature count collection counts. It will be giving a count result. Okay, this is the count. So feature count is already done, right? So next we had to, okay, after feature counts you can do multi QC again. So I'm not doing here, but you can do multi QC, and you can you can aggregate the result to a single report. Then the analysis part, like you can analyze the data easily. Okay, so here I didn't do because I had to finish fast, right? So I didn't do that. But in your, if you are doing a high end research, you can do that multi QC. After feature counts, you can do a multi QC and combine the result. Okay, then after feature counts, we have to do genome genome expression analysis. So for expression analysis, we are using DSeq2. Okay, so
Ma'am,
for that, huh,
ma'am, for multi-QC again, the input file will be feature count file.
feature count
Okay,
files. So
okay,
it will be like feature counts file. Okay, not summary file.
okay.
Okay, so both you can try. So whatever result you can, like, then yeah, then for genome expression analysis, we are using DSeq. Okay, so other tools are like Limma and Edjar. So both are good for doing RNA analysis. Limma actually before, for doing micro array analysis, we were using Limma, but it extended to nowadays it is extended to RNA-seq analysis also, and even Edjar and DSeq is almost same. Okay, almost giving same result. But right now I'm using DSeq. Okay, so DSeq, for doing DSeq, we had to download the data. Okay, so it's not in tabular form. I think it's not in tabular form. So we had to download the data. So it's okay. Save. Okay. Uh, okay. Everything, every data, like we just download. Okay, one by one we can add. Otherwise, it will be confused. Okay, we can add this. Okay, 47. Five. So it's not showing here. Otherwise, you can save it as uh, file. Save it as somewhere like downloads or desktop, anywhere. Downloads. Okay, then paste here. Save. You already exit. Yes. Then you can upload each data like this, like upload. Okay, upload like this. You have to upload each file like this, and you can can made it as tabular tabular format. Just save it as tabular format. Okay. Okay, so everything, every file you just download like this, or you can save like this, and you just upload same thing like this, and close like this. So then, okay, we can go for dseek. D seek two. So this is the DC2 tool. It mainly determines the differentially expressed features from count tables, because we are getting count tables from feature counts. I mean count data from feature counts. Then we can do, I mean, differentially expressed features from that count tables. So this is, we have to click here, then select data set per level. Okay, level we can say, and here we can select the name, if it is a drug data or if it is a anyway treated a treatment data, that name you can put here. So here I'm just typing drug. Okay, then here you can give the name, like if it is a control data, you can give that control. Okay, so we just downloaded six data, right? Three control and three disease, like treated. Okay, anything we can say now. Next data is like
Ma'am,
three. Ah,
ma'am, the question I asked you about feature counts data, that it was showing unavailable. Uh,
okay,
it,
then
it,
you just continue with ensemble data.
okay, okay,
Ensemble. Okay, so
okay.
ensemble, yeah.
I uploaded the last data, but the analysis failed. It shows
Okay.
error.
Then you just
Okay,
continue with ensemble data.
okay,
Ensemble data is always updating.
okay.
Yeah. Okay, then you just go. Okay, after feature count, just we are doing dseek. Then first we selected data set per level, then factor name, that depend upon your data set. Okay, that anything you can put, like for your understanding. So that is, here you can see effect drug X or cancer markers, like that you can add. So here, okay, factor level, specify a factor level, that is, if it is a control, you can do control or anything, or treated or normal, you can put normal also. Then okay, control, which data we were downloaded, 58, 59, 60. So that was like, I think 52, 53, and 54, I think. No, this this one, 147, 148, 149, we download it as a control data. Okay, so just we are selecting control plus select. Okay, then we are selecting other data name, that is, if it is treated, we can here for your understanding, we just I'm just writing treated. Okay, otherwise deceased or patient, or it's, we selected a liver cirrhosis data, right? So that name also you can add. So here I just putting a treated name, so treated. Then you can other data, that is, you can select 152, 153, and 154. These are the data, that patient data. So then uh, no, that is in the choice of input data, count data. Okay, This and all you can keep it as mm, default. Okay, then you can run the everything selected, right? Level, drag, control. So control that data you just select here. Okay. Treated. That also we selected. This one is optional. No need. Files have header. Yeah, if we have the data have header like okay. Yes. Then count data. Choice of input data is like count data. Okay. Correct. Method for estimate size factors. No need. That one parametric. Perform fee filtering. No need. Okay. Then you can run the tool here. So DSeq is running now. So here you can see the so here. Yeah, DSeq is feature counts is running and DSeq also running. Okay. Okay. So I'll show the DSeq result. Okay. DSeq result will be like this. Okay. So result file on data. So data will be like this. So gene ID, base mean, log to fault change value, standard error, where starts p value, and adjusted field value. So it will be like that, like this, like DSeq analysis result. So next the result will be plot. So this is the visualizing DSeq analysis. Okay, this is the PCA. Let's show the plotting. Okay, so till scatter plot only it is showing. So everything it will normally it will show like this. Everything it will come. I don't know why only three, four plot is showing. Okay. So this is the PCA plot. It mainly so okay you can see like this is the diseased group. So I'll just put instead of treated I just put diseased and control. So this is the control sample and this is the diseased sample. So this it mainly lets you visualize how the data groups based on a few principal components or dimensions that explain the highest variability. Variability means it's referred to as spread or spread, scatter, or dispersion, and the samples that cluster closely together in the plot means it's more similar in terms of gene expression, while samples that are further apart exhibit greater differences. Okay. Then next one is like heat map. So heat map mainly as a way to represent a matrix of data, and in our case, gene expression values. It shows it has like colors on the basis of colors, and the columns of the heat map are usually the samples, and rows are mainly genes. It gives us an easy visual of how gene expression is changing across samples, and while it can be plotted using all genes, it usually makes more sense to plot and using a set of highly varying genes. And clusters of samples with similar expression patterns may represent distinct groups of condition. Okay. Then next is like scatter plots. Okay, scatter plots. Mainly, this type of plotting is using dots to represent values for two different numeric variables, and the position of each dot, like on the horizontal and vertical axis, indicates values for an individual data point, and values tending to rise together indicate a positive correlation for okay. So here you can see like black color means gene EST, and this is like red fitted, and blue color is like final. Then this is like histogram. Histogram means I think everybody knows like histogram is a chart that plots the distribution of a numeric variables values as a series of bars. Yeah, so p values and frequency. Yeah, this is like MA plot. So MA plot, control versus disease. You can see mean of normalized counts x-axis, and this is log fold change. This plot visualizes the differences between measurements taken in two samples. Like genes with similar expression values in both normal and treated samples will cluster around m is equal to 0 value. And that is gene expressed with no significant differences in between treatments. Here you can see no significant descent. This is like upregulated, and this is like downregulated genes.
Dr. Vijana, one question is there.
Okay,
Ma'am, what is adjusted p-value in DSeq results? Adjusted p-value.
that I will discuss further, while discussing that result of DSeq. I'll discuss what is p value, what is log fold change value, and all. Okay, so next we are anot. Okay, this is done. Okay, DC result done. So next we had to do the annotation of this DC result, annotation of this gene. Okay, so for that we had to use this annot DC to output tables, that is append annotation from GTF to differential expression tool output. So you have to click this. Okay. Then tabular output of DSeq. Okay. Yeah, DSeq. It's like feature count. No, it's saying feature count summary only. So yeah, feature count summary. Then input file type is like DSeq2 edge or lemma result. Okay. Then uh, you can reference annotation file, so that is already it took otherwise you can browse the data set here, genome human GTF file, then you can run the tool. So here you can see the result. Okay. Oh, yeah. Okay, here you can see the result of annotation. Okay. You can see here. Okay, it shows the after annotation, you will get the gene ID here. Then what is the region, like protein code? Is it a protein coding region? Uh, and everything it shows here. So you can download this data. This is the annotation result of that gene expression uh, things, and here you can see the result. Okay, then you can copy this file. You can save it to XLS file or you can copy the file. Okay, then you can open a XLS file. So Excel file. And paste here. Okay, so till this, I'll say the analysis steps. First, we are downloading the data from Geo database. Okay, then we are uploading the data to Galaxy. Then we are doing quality control using fast QC. Then after fast QC, you can do multi QC, that is optional. Then you can go for trimming. Okay, trimming, that is you can use Trimmomatic, Trimgaller, etc. So here we used Trimmomatic. Then we are aligning the data. I mean, we are mapping it with the reference genome. Okay, so since it is a human genome, we downloaded human genome from Ensemble database and we downloaded the GTF file also. So we are mapping the genome using HiSat2 tool. Okay, so till mapping over, then after aligning, we had to get the count data. So for getting the count data, we are using feature count. Okay, so using feature count, we are getting the count table. Then after that, after getting count data, we had to continue the expression analysis. So for that, here we are using DC2. Okay, so DC2 analysis also over, and after that, annotation of that gene ID. I mean, uh, like you already I showed, right, in DC. The information is not there actually in DC data. This one, not plot. Okay, the gene ID is there, but information is not there. Okay, so for that we are annotating this data. We are doing that annotation. So after annotation, we are getting this data. Okay, we are getting the gene ID and I mean information about that protein. If it is a protein coding region, it shows here. And okay, everything. Okay, I'll write header file here. Insert. Okay, so here it is a gene ID. This is the gene ID. So by looking that I mean DSIC file, you can find this gene ID. Then next it is base mean. Okay, base mean. Then this is the log to fold change. Log to FC. FC value. Okay. So next is like standard error. Okay. Then then the p value. Okay. P value. Then it's like adjusted p value. Then it is CHR chromosome. Then starting position of that gene, and this is the end position of that gene. This is the strand information of particular that gene. Then this is like protein coding information. That okay, coding information we can add coding information. Then this is like gene name. So here, okay, by this one you can save in your desktop for further analysis. Actually, after doing genome, I mean DSeq analysis, we can do gene ontology or pathway analysis for doing function. Okay, that is like functional analysis we can do in galaxy itself by using go seek and path view. But here we are not doing that one, we are not using that one, that tool. So we here I'm just using go profile. G profiler. Okay, this database is using for this is a web server for functional enrichment analysis, but it will show every details like pathway analysis and gene, which pathway is enriched in this gene, everything it shows. Okay, so we are using, I mean till DC2 or annotation we are using Galaxy. So after that, for finding gene ontology, the functional analysis, we are using G profiler. So here the G profiler. Okay. So before that, I'll describe what is p-value and log2 fault change value. So actually fault change means it's defined as the ratio of the difference between final value and initial value, that is divided by the initial value. That is fault change value mean greater than 1.5 or 0. uh, it means its gene is upregulated. Okay, it's if it is less than 0, it means it's down regulated. Okay, so log 2 FC means log 2 of B minus log 2 of A. It is mainly a measure of describing how much a quantity changes between an original and a subsequent measurement. Mainly, you can do like if it is greater than 0, that is here you can see. Okay, if it is greater than 0, it means the it is then is upregulated, and if it is less than 0, that is exact. If we can like exactly, if we are telling 0.66. Okay, if it is less than 0.66, otherwise or 0, we can say the gene is down regulated. Then next is like p value. Okay, p-value means it's a measure of how likely are to get this spot data if I mean no differences existed. Okay, therefore a small p-value indicates that there is a smaller change of getting this data if no real difference existed, and the uh, and before you decide that, if we can say like a p value is Okay, if it is a small, we can say like it's very significant. Okay, that is if it is like less than 0.05 or equal to 0.05 or less than 0.05, we can say the value is significant for that. Then, okay, so here before going Go Profiler, here we had to, okay, do further analysis. So here you can see, okay, here you can see in some cases you can see NA data. Okay, so that gene information is not available in this case. So that means that, and so for that we had to remove that data. So here also you can see NA, NA. Okay, so that means gene information is not available. So for removing that data, we had to click here and data, then we had to filter it. Okay, then text filters, then does not equal to NA. Okay, yeah, then it filtered. You cannot show. Yeah, NA is not there. Okay, so same thing, you can filter here also p value if it is containing a Na value, but Na value is not here, but in some cases it will be present, so you can avoid that by unclicking the simple. Okay, then okay, here it is not present, so I just, okay, then for analysis, this value is important for analysis. Gene ID, then p value, and log to fc value. So these are the important things for doing gene ontology analysis. So here we are copying this data into, okay. Then we are copying this thing. Copy, okay. Then p value, p value. So I already said like log, if it is like more than zero per, I mean greater than 0% zero means its gene is upregulated, and it's if it is less than zero means it's downregulated. So we can filter like that. Okay, data. Okay, filter. Okay, greater than zero. Yeah. These are the upregulated genes. Okay, these are the upregulated gene. So here we can make it as significant p value. So here how to change p value? Okay, less than or equal to 0.05. It means it's significant. Okay, so here you are getting the upregulated genes list. So this you can copy here, copy and paste it as, upregulated. So here you can name like rename upregulated up. Okay. Then you can click here again filter on the basis of like less than 0. Okay. It means these are the down regulated genes. Okay. That also you can click here. Copy. Okay. Then you can do a gene ontology analysis using Go profile. So I think some will be using David. So many functional enrichment analysis tools are available, right? So David also very good tool for doing gene ontology analysis and pathway enrichment analysis. And even Go profiler, it also will gives a good result. G profiler. So here you can okay, here you can type this I mean, so you can just copy everything. Just copy. I'm copying just some data. Then you can give paste here and run query. It is very easy tool. So it will show the result here. It is taking time here. It's yeah, shows the result like this. Okay, so it's running now. It's running. Okay. So everything like log p value. So keg analysis, ontology terms. This is the term ontology term name. So it's coming down actually. It's here. It's it's very net is very slow. That's why. So you will get everything like pathway information and ontology term and term names. This is which regions, which activity, everything you will get it. Okay. So here you can detailed result also, it will be available. Okay, detailed result you can see here uh, which term it is, like term name, then gene name, process, kidney development, which process it is, then term name, focal. This is the pathway information. Okay, KEG pathway information. Then yeah, this is the disease pathway information. Yes, Kinextracelematis. Yeah, this everything you will get it here. Like if you're using G profiler, that David also you can use. Then I think so many other tools are available, but I think G profiler and David is easy to use. Other tool I didn't use it, but I think compared to other tool, it will be very. I mean, it shows everything. Okay, so yeah, today the analysis is actually over. So from starting itself, I'm again saying the thing. First, we are downloading the data from Geo database. You have a own data set. You can upload the data. And first, we are starting the quality control that is using fast QC. Then we are trimming the data, that is using Trimomatic. Then we are aligning the data using HiSat2. That is, and for doing HiSat, we are downloading the FASTA file from Ensemble database, and GTF file also we downloaded from Ensemble. And after getting alignment, we had to we are counting the data, we have to get the count data of that alignment. For that we are using feature count. Then after feature counts, we are next we are going expression analysis. That for that we are using dseq2. And after the dseq analysis, we are annotating that file using dseq annotation, that tool. Then after getting the file, we are downloading the data, and we are checking the pathway information in G profiler. Okay, so actually, this transcriptome analysis is over now. Uh, if you have any doubt, you can discuss in group. While doing anyway, you will get a confusion and you'll get a doubt. So you can ask in group. I think group will be active always. So you can ask in group.
So I think the session is open to
Yeah.
questions. If you have any doubt or questions or anything, one comment is coming. I think
If you want to do in Galaxy itself, that also you can do. Some tools are available, but I didn't use that one. But path view and go seek are there, so that one also you can try for doing this ontology terms.
so.
But it is very easy, like G profiler and David, it is very easy to use. So just you just copy and paste it here, and it will show automatic result.
Bevin Nishant is commenting, we need to practice, ma'am. Overall experience was very nice.
Okay.
So like that.
So you also practice well, and if you are getting any confusion, you can type in group. So
Okay.
just try other tools also. Like we used HiSat2 for alignment. So you just try star also. So you just try star, then you just continue feature count, then dseq2 annotation file, like that. So instead of HiSat2, you just try star.
I think you people are free to contact Dr. Vijana personally also. So it is not about the
Yeah.
company or anything. You can directly contact you for your any help, Dr. Vijana. So I hope the
Anyway, sorry for this much gap. I mean, it's my fault. It's my personal fault. Actually, I took so many days to complete the transcriptive analysis. So for sorry for that, actually.
any
But
exercise for you from you to for us to practice. One question came. Exercise, if some exercise.
same data set you use, and you just continue the analysis. I think it will work for you, because last data set was not working for me. That's why I changed the data set. So you just use this data set and continue the analysis. So just complete the analysis and let me know that.
Okay, let us wind up the program.
Yes.
If any more questions, we can. As one comment came actually before DSIC2, we downloaded the feature count file and edited it in WordPad. That part, can you repeat, ma'am?
Same thing I followed. Same step I followed here also. But the data set was different. So that set was not working. If it is working, you can try that data set, but it was not working for me. I don't know. If it is working for you, you can use that. Otherwise, you just change the data set. So many data sets are available in geo data set, that is transcriptome data set. So you just type in, okay, I use that SRP 240 but you can use any data for training purposes. Okay, so you just type RNA-seq in geo, so it will show so much of so many data. Then you can use that data for analysis.
Okay, ma'am. Okay, ma'am. I will change the data set and try it like that. The command came.
Okay,
So
that will be good because it will take time, because if it is failing, just change the data set. If it is your work, not like this data set, if you are doing a data, like if you are doing a PhD or something like that, if you want to do a same data set, you can, if it is failing, you can change the pipeline. Okay, if it is I mean, if it is failing the particular tool, you can change the pipeline and change, I mean, uh, do the analysis.